Okay, so this video is one of the most important videos in the entire trigonometry course. It's right up there with the unit circle and the general definition of trig functions. And in fact, you could argue that this video is even more important than all of the videos in this course, except maybe the general definition of trig functions. It's hard to get any more important than the definition of trig functions. But it potentially holds its own special place as being the most significant video because it incorporates both the extremely important graphs of sine and cosine functions, as well as the relation of the sine and cosine functions and thus trig functions in general to the circle, which, as I mentioned, is one of the 4 or 5 main things you want to learn in trigonometry. One of those is the relation of the trig functions to circles, circular motion, anything circular. Okay, so in this video, we're going to start chapter 4, which is on the graphs of the trig functions. And in this video, we're going to go through the first section, which is on the graphs of the sine and cosine functions. Okay, so here's the opening image for this chapter. Looks pretty cool. It's different progressions of shading of the moon. Phenomena that repeat in a regular pattern, such as average monthly temperature, fractional part of the moon's illumination, and high and low tides, can be modeled by periodic functions. Yeah, so when they say periodic, that's not talking about like a sine or cosine function or a trig function specifically. You can have a periodic function that isn't trigonometric, but focusing on sine and cosine functions, one of the reasons why this video is so important, this is one of the pillars of trigonometry to understand the graphs of the sine and cosine functions, is that those are periodic functions that can be used to model so many phenomena in nature, in physics, and engineering. The periodic pattern of the sine and cosine functions is so fundamental to the universe. I can't understate that. You know, later in school, you're going to learn something about the Fourier transform, and this theorem shows that you can take absolutely any periodic pattern, no matter what it is, and decompose it into sums of sine and cosine functions. Okay, but it starts by talking about what a periodic function is. It says phenomena that repeat with a predictable pattern, such as tides, phases of the moon, and hours of daylight, can be modeled by sine and cosine functions. These functions are periodic. The periodic graph in figure 1 represents a normal heartbeat. Okay, so yeah, I think we all intuitively understand what periodic means, what a periodic function is. It's just a pattern that repeats indefinitely. Okay, so here's like the pattern of a heartbeat. I'm not sure what's being measured here. I guess just it's the noise. So this is like measuring sound, and you can see it's this pattern that's repeating over and over and over again. And there's a lot of different functions that are like that. And we're going to see the sine and the cosine functions are like this, as well as all of the other trig functions. All of the trig functions are periodic. Now, when you're looking at a function that's periodic, what you can think about is you can pick out the pattern that's repeating. So here we could see that, you know, we could say go from there to about there, and in between these two marks, there's the pattern that's repeating, right? It's just the same exact pattern repeating over and over and over again, all the way to the left, all the way to the right. And that's how mathematically you can think about what the definition of a periodic function is. So it says periodic functions are defined as follows. So before we look at this definition, in algebra, we talked about function symmetry. There was different kinds of function symmetry. If you had an even function, that means that if you have f of x, if you plug in f of minus x and you simplify, you get back the original function. Okay, there is an odd function where if you plug in f of minus x and simplify, what you get is minus f of x. These were two forms of symmetry. A periodicity is another form of symmetry of a function. And it goes like this. If you take f of x and you plug in x plus some distance, and now this distance could be, you could put a positive or a negative p, whatever, then you get back the original function. That's what periodic symmetry means. And in fact, to be more specific, you could take any integer multiple of that p, right? And you get back the original function. Where n can be, you could look at this however you want. Maybe p is always positive, or you could make p negative, whatever. You could go, this could be negative or positive. You can go to the left or the right. It's just this same integer multiple of p, you get back the original function. So if we come here, what they're saying is that if you come to any point on this graph, start here, and then you move to the left or the right an integer multiple of the period, you're going to get the exact same function value, right? If I go 2 periods, I get the exact same function value. You see? So that's the idea. That's periodic symmetry. Okay, so that's the mathematical definition. You could see f of x is equal to f of x plus np for every real number x in the domain of f, every integer n, and some positive real number p. So they say that p is positive, but you could define it however you want. You could maybe say p could be positive or negative, but n is restricted to positive integers. But this is, they make n any integer, even negative integers. So, okay, but it says the least possible positive value of p is the period of the function. So you can't say that, I can't say that if we're starting, you know, here, I can't say that, okay, this distance is p. No, because I could make it, I could also say that this distance is p, right? But I can't go any smaller than this. There's no way for me to find a repeating pattern within here. So this is p, okay? So it's the value p is just a number, but it corresponds to the x-axis, the independent variable axis. It's a unit, the period is a unit of the independent variable. Okay, so now with that, you can see how trig functions are going to be periodic, because I'll use the unit circle definition, but you know, remember, we don't have to use the unit circle for trig function definitions. But because it going in the negative x, the independent variable is theta, right? Is the angle, and then the dependent variable is the trig function. Going in the negative or positive direction all the way to infinity, you're repeating every single full rotation. It starts over again, right? Trig functions, once you get past a full rotation, it just repeats the same values again. And this is for all trig functions, right? Now, yes, you do have some trig functions that don't exist they have asymptotes, right? Things like that. But still, it's still repeating. You could be repeating and have like a point where the function isn't defined, has a vertical asymptote or whatever, right? So like tangent, we'll talk about what functions have vertical asymptotes and whatnot, but you know that like tangent isn't defined at some quadrantal angles. Same with cosecant and secant and cotangent, but that doesn't affect the fact that they're periodic at all. It's good because it's going to be a repeating pattern, even where the points where the functions don't exist is kind of part of that pattern. Okay, so now what you can think about is that, so what's the period of the trig functions going to be? Well, okay, let's think about the independent variable, which is the angle, if we think in radians or even degrees, but let's focus on radians. It's going to be 2 pi, right? Once you get to 2 pi, well, it's going to be n times 2 pi. Any positive or negative integer times 2 pi, well, no, that's not right. I'm sorry, that's not right. The period is going to be, if we go by this definition, the period p is a positive number, and it's the smallest possible value that encloses the repeating pattern. So the period is going to be 2 pi. But then if you come to the definition here of how periodicity corresponds to functions, you could take f of x and plug in any integer multiple, positive or negative integer multiple of 2 pi, and you'll get the same function, the original function back. Okay, now when we get to graphs of functions other than the sine and cosine function, I want to say, I'm kind of forgetting, but I want to say maybe tangent actually has a smaller period than 2 pi, and we'll see why that is. And it might be the case with the cosecant and secant functions. But, you know, in general, though, we can just think about it that you could, if you were learning about trig function graphs for the first time, we could start by assuming that, okay, I'm sure all of them, well, okay, how about this? 100%, there's going to be no trig function that's going to have a period that's greater than 2 pi. And if we had to guess, if we didn't know any better, we would start by assuming that all of them have a period of 2 pi. Okay, but the sine and cosine functions, there's no domain issues anywhere, and they do have a period of 2 pi. So, which makes sense because you get, so, all right, you've got, there's the radius, x, y, you get, so sine is opposite of hypotenuse, so it increases to 1, then goes back down to 0, then goes down to -1, then comes back up to 0. Yeah, then repeats again. Okay, but like tangent y over x, that goes from 0 to infinity, and then -infinity to 0, then 0 to -infinity. Yeah, we'll take a look at it. I believe tangent has a period, ends up having a period less than 2 pi just because of the way the definition of it works out, the way the numbers work out. But you can see sine and cosine, if we follow sine and cosine through all the quadrants, it's going to be a unique graph. You go from 0 to 1, then 1 to 0, then 0 to -1, then -1 to 0. Then you start back increasing in the positive direction towards 1. Tangent was, okay, so tangent goes 0 to positive infinity, increasing towards positive infinity, then -infinity to 0, then 0 to -infinity, then -infinity to 0. Maybe the period's 2 pi. We'll see. We'll see as we go. But, okay, but the sine and cosine functions repeat every 2 pi. Therefore, the sine and cosine functions are periodic functions with period 2 pi for every positive integer n. And yeah, so there you go. Sine of x is equal to sine of x plus, okay, they're saying positive integer n, but it could be negative as well. Right, like sine of 2 pi is 0, sine of -2 pi is 0. So yeah, n can be a negative integer as well. You take any sine value, sine of 32 degrees, sine of pi over 3, and then you add or subtract from that some integer multiple of 2 pi or 360 degrees, you're going to get the same exact value out. And that makes sense. It's exactly what we know about the definition. If you have coterminal angles, you have the exact same trig function values. And that's what makes them coterminal. If you add or subtract any integer multiple of a full rotation. And it's not like that's not the case for trig functions that potentially have periods less than 2 pi. No, it's just that it ends up being the case that you could find a smaller value than 2 pi where they're periodic. But they're all technically periodic on 2 pi, all the trig functions, 100%. But the numbers work out to where for some of the other trig functions, you can actually go like plus or minus pi, and you end up getting the same value. Like, okay, so tangent is, yeah, it's like this. So tangent is opposite over adjacent, but then when you come to the negative angle, you get opposite over adjacent, but it's a negative divided by a negative, so you get the same value. Yeah, exactly. These two, the tangents are the exact same. These two angles here, right? Because y divided by x, positive y divided by positive x, that's tangent. Here, negative y divided by negative x, that's also positive. But the sine, okay, so opposite over hypotenuse is positive sine. Here, opposite over hypotenuse, that's a negative sine. Now you might say, well, okay, but you get this here, right? This is the same value, opposite over hypotenuse. These two are the same, but it ends up, that's true, but you can't find a repeating pattern. Like, it's because it ends up, it's not like this. When you get here, it bounces off the x-axis and goes back positive again. So we'll look at the other trig function graphs as we go. But okay, the graph of the sine function, cosine is very, very similar. Just note that. But the graph of the sine function, it says we have seen that for a real number s, the point of the unit circle corresponds to the, yeah, so on the unit circle, it's we can think about the coordinates of the unit circle correspond to sine and cosine, but we're tracking the y coordinate when it comes to sine on the unit circle, right? So, okay, if we okay, so there's r, x, y. Let's say this is the unit circle. Again, the sine function, it starts at 0 and it's going to go up to 1, then come back down to 0, then go down to -1, then come back up to 1. And that's what they're pointing out here. Now, when you think about this in terms of angle, we're going to talk about this in radians. When you're going from an angle of 0 to pi over 2, you go from, then the sine function goes from 0 to 1. We're tracking the y coordinate. This is the unit circle. When you go from 0 to pi over 2, then the function value goes from 0 to 1. When you go from pi over 2 to pi, the function comes back down from 1 to 0. Then when you go from pi to 3 pi over 2, the function goes down to -1. And then when you go from 3 pi over 2 to pi, the function comes back up to 1. And then it repeats that exact same pattern again, and then again, and then again. Or we could go in the other direction. We could go from 0 to -2 pi. It would go, the pattern would repeat going from -2 pi to 0. The pattern going around the full circle would repeat going from -2 pi to 0. But if we started at 0 and went backwards, we'd be following the sine curve through a period backwards. We'd go from 0 to -1, and then back up from -1 to 0, and then from 0 to +1, and then from +1 back down to 0. Okay, so there's the graph. And they show a period in the forward direction. Here we went around the full circle. And you see, you know the question of, well, look, we got the same value, and we got the same value here. So isn't the period going from, if this is the same value, these have the same height, isn't the period going from here to here? Isn't that a period? No, because look at the pattern. So yeah, there you get the same value, but you can't say that this pattern is repeating. That's not what's repeating, right? It's only a full rotation that repeats. Then if you continued on to the right, you'd start up again. And see, and then when we went backwards, you're going in reverse, but the pattern repeats going from -2 pi to 0. So you can't, the idea is you can't say, if I tried to say that this was the period, so let's say, what is that? That would be pi over 2, maybe. The period's pi over 2. These are about pi over 2 apart because we went 90 degrees, right? Okay, so let's say the period is 90 degrees. Well, then what I'm saying there is that if I take any multiple of pi over 2, or 90 degrees, and I start at it's a random x value, and then I add an integer multiple of that, plus or minus, I will infinitely in either direction get the same value. Okay, so let's go pi over 2. So I went pi over 2 from here to here. It worked. Let's go pi over 2 from here to here. I don't get the right value. It's down here. So that can't be the period. It's only at 2 pi where I could start at a point and I could go infinitely 2 pi in an integer multiple of 2 pi in either direction, and I will consistently, no matter what, get the same, be on the function. Okay, so what they did was they plotted some of the special angles. So x is like the radian values corresponding to some special angles, got the trig function values, plotted them, and then connected the dots. And that's how you get you figure out that it's this curve here, right? That's all they did. That's the idea. If you want to do this on your own, which we'll do, you plug in, you create a table with x values at a bunch of different special angles in all of the quadrants, so you can get the corresponding sine value, and then you plot it, and then connect the dots. Okay, now we know that we've already talked about, but the sine function its domain is all real numbers. You can plug in any value, quadrantal angle, whatever, and it's going to exist. So this is continuous everywhere. And so the domain is all real numbers, but the range is, we've already talked about, is just -1 to 1, including the endpoints. Okay, it says this graph is called a sine wave or a sinusoid. And actually, the cosine graph is also called a sinusoid. The cosine graph is going to be called a cosine wave, but they're both called sinusoids. And you'll see why that is, because it's the cosine is literally the exact same thing as the sine. It's just like shifted to the left or the right, whatever. If you, instead of starting here, it's like it starts up here. It's the exact same graph. In fact, you can create like any shifted version of a sine graph or cosine graph by adding a sine and cosine together. They're like twins. That's the best way to describe the sine and cosine graph. They're like twins, identical twins. Okay, what are some other features of this graph? The x-intercepts. So real quick, just note that we're strictly talking about sine of x or theta, whatever. Unshifted, unscaled, just as basic as it gets. That's what we're talking about at the moment, okay? Just keep that in mind. All right, so we talked about its domain, its range. The x-intercepts, first just sine x, the x-intercepts, we can see those repeat every pi. So it's an n times pi, where n is any integer. Positive or negative integer, n times pi, that's where the x-intercepts are going to be on the sine graph. Okay, so we know it has it's periodic, right? It has periodic symmetry with period 2 pi, but it also has another form of symmetry, another form of function symmetry. The sine function is an odd function, which means that so you plug in minus x, and that equals minus f of x. So that means that sine of minus x is equal to minus sine of x. And the way you view that is that it's symmetric with respect to the origin, which means that so if you pick any point, let's pick a point over here, and you flip about the x and the y, and you're back on the graph. So that means that you could take any point x, y that's on the sine curve, and then if you, with that point, the x's could be positive, it doesn't matter, x and y are positive, negative, whatever, as long as it's on the graph, and then you multiply the x coordinate by -1, and you multiply the y coordinate by -1, and you will be on the graph. That's the meaning of an odd function. If you need to do a review on graph symmetry, go check out the algebra playlist. Graph symmetry and function symmetry. So like circles aren't functions, but still they have a symmetry, right? Okay. The sine function is related to the unit circle. Its domain consists of real numbers corresponding to angle measures or arc lengths on the unit circle. Its range corresponds to y coordinates. Yep. Consider the unit circle in figure 2 and assume that the line from the origin to some point of the unit circle is part of the pedal of a bicycle with a foot placed on the circle itself. As the pedal is rotated from 0 radians on the horizontal axis through various angles, the angle or arc length giving the pedal's location and its corresponding height from the horizontal axis is given by sine x are used to create points on the sine graph. Okay, so I don't want to get too mixed up with when they talk about circular functions. We're ignoring the term circular functions, but what they just described here, where you want to think about how the you know, it's really important that you think about the marriage of the sine and cosine graphs with the circle, specifically the unit circle, but it doesn't have to be a unit circle, and I'll talk about that. So we'll come back to what they just talked about here in a second. Actually, no, here we go. So perfect. So take a look at this. Okay, yeah, this is extremely important. This is one of the most important figures in the entire textbook, in my opinion. And you can view both the sine and the cosine function this way because, again, they're identical twins. So this is so important because, again, this pattern here, this sinusoid pattern is just so fundamental to nature. This is a shifted sine or cosine. This pattern is enormously important. Okay, and so that's why it's important that we learn this graph. But it's also important that we understand the connection of trig functions with a circle. It's really the sine and cosine functions have the main connection, but really all trig functions are connected with something circular. Okay, the sine and cosine functions are probably have the biggest connection because that's the actual, on the unit circle, those the coordinates on the circle are the value of sine and cosine, right? But yeah, you really want to, whenever you think about a sine or cosine function, here let's talk about the sine, you want to be able to, what that paragraph just described, you want to think about how, as you're going through the sine function, you can also, in the back of your mind, think about how you're walking around the circle, the unit circle. But, I don't want to say unit circle because we're going to see, like we could say, so y is equal to 3 sine x. Well, in that case, the amplitude here is going to be pushed out. Instead of plus or minus 1 being the range is going to be plus or minus 3, and we'll have a circle with radius 3, right? So, yeah, the definition of the trig functions is you can only do that with a unit circle, the definition. But it's not like, you can't venture out when applying the trig functions, you can't venture out from a unit circle, okay? So, but thinking about we're thinking about the unit circle here. Yeah, so as you go down the sine function, you're also walking around the unit circle. We just went to pi over 2. Then we're going back down to we just finished a half rotation. Now we're going to the 3/4 around the circle, right? Okay, and so what that paragraph in the previous page described was that you can think about it this way because with the unit circle, again, the coordinates of the point on as the angle, as you're going around, as the angle around the circle is increasing, it's the literal coordinates of the point on the circle that are corresponding to this height on the graph, right? Like this is, if you put a point here, and so that had an angle tied to it, right? Here's an angle. And you started, like we made an angular velocity, like we actually made this start moving with a certain angular velocity. Well, then that point would, if this is the sine graph, that point would be vertically lined up with wherever you are in the sine graph, right? They would be lined up. As this went around, it would get, when you got to pi over 2, this would be at 1. Then you'd walk back down to 0, and this would vertically follow it all the way back down to 0. As you went down from 0 to minus 1, this would go vertically aligned all the way down to -1. They would be vertically married to each other. So you see that intimate connection between the circle and the sine graph here, and similarly we'll see with the cosine graph. Okay, now this, when we actually think about tracing an object, like thinking about the concept of angular velocity, it's really important to, we're going to see applications where, you might be modeling something in real life that follows a sinusoidal pattern. But then you'll hear there's 2 frequencies that will be mentioned in regards to something that follows like a sinusoid pattern. It's they'll say just regular frequency, but they'll also say like the angular frequency of the sinusoid and you think angular frequency, well, where is there an angle? Well, okay, well, when they talk about regular frequency, they're talking about, so, if we're following something with respect to time, you can think about there's a, when you say frequency, that has to do with something that's repeating, a repeating pattern. How often does the pattern repeat? That length of time is a frequency, right? And so what they'll talk about is how long does it take to repeat the sinusoidal pattern? So to go from here to here, how long did that take? That's like the regular frequency. But then they'll also mention an angular frequency, and what they're talking about is with respect to, how long, what's the corresponding angular frequency? Okay, so here the regular frequency and the angular frequency would be the same, but you might have a, you might have a sinusoid that its period isn't from 0 to 2 pi because you've modified it, right? If you take a sinusoid and you multiply the x by something, you're changing the period. So I don't want to get too deep into this right here in this video. I'll talk about this in another video, but with a sinusoid, you can look at a sinusoid. You can look at any random sinusoid and you can think about it has a period, and the period doesn't have to be 2 pi, again, because you can multiply the x, the argument times a number and change the period. It has a period. It has a frequency if it's related to time. So if this is the time axis, then the frequency is going to be the length of time it takes to go one period, which is, I don't want to get too much into that here, but there's also then the angular frequency, though, where you're thinking about, okay, in the background, we can imagine we're going around a circle, right? So what's the angular frequency? That doesn't have to be always equal to the actual, you can think about it like linear frequency on the graph. Okay, and I might not have explained all of that very well. If you're confused, don't worry about it. We're going to go through this slowly and in full detail in upcoming videos. Okay, the graph of the cosine function. The graph of y is equal to cosine x in figure 5 is the graph of the sine function shifted or translated pi over 2 units to the left. So, yeah, we took the sine function and you can see you shifted it to where this point was the start point for the sine function, right? We started with the sine function going up like that. Here, now we're starting here. We've shifted it to the left pi over 2 units. That's it. Okay, now so here they put some special angles, plug that into the cosine function and plot it, and that's how you can see the shifted curve. Now you might be wondering, well, I know from algebra how to shift a function. Okay, so I can shift sine to the left by a certain amount if I want to go to the left, I add. So I want to go pi over 2. All right, so I just shifted the sine function to the left by pi over 2 radians. And they're saying that that's equal to the cosine function. Is that right? Yeah, that's right. That's exactly right. All right, this, like the sine function, the domain is all real numbers. The range is plus or minus 1, including the endpoints. We're just talking about cosine x, unshifted, just the bare bones cosine x. Okay, and the x-intercepts in this case are going to be any odd multiple of pi over 2, odd integer multiple. So you can see you got pi over 2 minus pi over 2, then 3 pi over 2 minus 3 pi over 2, and so they represent that, that's shown here, 2n plus 1 times pi over 2, where n is any integer, positive or negative. Those are the x-intercepts. The period is 2 pi. You can see that's the smallest you can make an x interval to create a repeating pattern is 2 pi. Now, okay, so it has periodic symmetry, but like the sine function, it also has another form of function symmetry. The sine function was an odd function. The cosine function is an even function, which means that f of minus x is equal to f of x in this case. So cosine of minus x is equal to cosine x. And that, you can think about that as it's symmetric about the y-axis. So you pick any point, you flip about the y-axis, and you're back on the graph. You pick a point here, flip about the y-axis, you're back on the graph. And that means that you take any point x, y that's on the graph. These could be positive, negative, whatever. And if you change x to minus x and leave y, don't touch y, you're back on the graph. Okay. So it says now, techniques for graphing amplitude and period. Techniques for graphing amplitude and period. So, okay, the examples that follow show graphs that are stretched or compressed, shrunk either vertically, horizontally, or both when compared to the graphs, the base graphs. So yeah, we know from algebra that you can transform graphs, you can translate them vertically, horizontally, you can stretch them about the y or the x-axis, you can flip them about the y or the x-axis. So, okay, it says graph y is equal to 2 sine x and compared to the graph of y is equal to sine x. What you're doing here is you're stretching this about the y-axis by a factor of 2. So remember, when you do that, if you need to go review translations of graphs, go to the algebra playlist. I mean, it's a kind of a tough topic on its own. Not tough, but there's a lot to learn there. But if you want to do this, if you want to take the graph x, y, so let's say we're starting with cosine or sine x, and you want to, this is what you want to take every point and just multiply every point by every y coordinate by 2. That's stretching it by a factor of 2 about the y-axis. Then what you do is you go to the equation and you multiply each of the variables you're interested in, so there's only one y variable out front, by the reciprocal of that. And so with this, if you multiply both sides by 2, you get this. So that's what when you just put a factor out front like that, this is what's happening right here. You took every point on the sine x graph and just stretched the y by 2. Okay? And that's what they call you've changed the amplitude. You've doubled the amplitude. That's another way of looking at it. This is the technical way of looking at it. Every point, it's not like it's just been these peak points that have been stretched. Every point has been stretched by the y-axis by a factor of 2, but when it comes to sinusoids, you think about the range of it. So the range of the sinusoid. So the basic function goes from -1 to 1. That's the range. Well, that's what the amplitude is. It's not the full. It's half of the full. So it's not this distance. That's not the amplitude. The amplitude is the distance above and below the x-axis you're going. Okay, so we've added this term amplitude, and you can think about what we're doing here is these graphs are so important. They name features in the graph, right? We don't do this for like the graph of the square root of x or or other graphs because they're not as important. But these graphs the graphs of the sinusoids are so important. They've got names for all of the features. Okay, like we know the period is the repeatable pattern x independent variable distance. We know there's an amplitude, and we know how we can change the amplitude by with a function. You don't have multiple y values, so we change the amplitude by. We know how we can adjust the amplitude from it starts the base function is at plus or minus 1, but we can multiply the front of the sine function or the cosine function by whatever amount we want to change the amplitude. Okay, now it says here we can think of the graph of this is a vertical stretching of the graph, or you can shrink it, right? You could multiply it by 1/2 to change the amplitude from 1 to 1/2. Okay, so the graph of y is equal to a sine x or y is equal to a cosine x when a is not equal to 0 have the same shape as the original graphs, respectively, except that the range is changed. Yeah, it's the same exact shape. You just scaled it, right? So, and the way you can look at this is, so this has a amplitude of 2. Well, you could draw a circle of radius 2 off to the side, and it would have create that same tracking pattern where you could track the vertical the vertical points on that circle of radius 2 you could walk around the circle as you walk along this sinusoid. Now, at that point, I think you're shifting away from the definition of trig functions, right? That when you think about the definition of trig functions, that really concerns the unit circle. The point I'm trying to make, though, is that this is still, you can associate this intimately with a circle still. This is going to have a angular frequency. If you're dealing with something tracking time, this is going to have an angular frequency, even though it's not a unit circle anymore, as well as a regular frequency and etc. Okay, now while the coefficient out front of the sine of the cosine affects the amplitude of the graph, we can also, so that was stretching about the y-axis, but we can also stretch about the x-axis by multiplying something in front of the x. And this is going to affect the period, right? So the standard period is 2 pi, but if we go from a standard sinusoid, let's say, okay, and now let's say we stretch it about the y-axis. Well, we didn't change the period, right? But if we multiply something by the x variable and let's say we don't change the amplitude, and we get, we're still going plus or minus 1. Let's say we shrunk it about the x-axis. We're still going plus or minus 1. Well, look, we've changed the period, right? It's not repeating at 2 pi anymore. It's repeating at something less than 2 pi. So it says consider y is equal to sine of 2x. So yeah, we know what's going to happen here. If you go review the translations of graphs, if you want to stretch about the y-axis a factor of 2, you multiply y by 1/2. And so when you multiply both sides by 2, you get 2 sine x. And it's the same with the x variable. If you want to stretch about the x by a factor of 2, you multiply each x variable. Here there's only one. We're just dealing with one y and one x in the function y is equal to sine x. But since they multiplied it by 2, then it's going to stretch the x variable by 2, then it's going to stretch the function about the x-axis by the reciprocal of that. So it's going to shrink it actually by a factor of 2. That's how the translations of graphs works. Again, if you need to, go check out those videos in the algebra playlist. So what happens here is effectively when you do this, you started with x, y. That's y is equal to sine x. Every single point is at x, y. When you put this 2 out front like that, you've changed it to where you've multiplied every point's position, x position, by 1/2 and didn't touch the y. That's what you've done. So you're going to shrink it. You're going to squeeze it in like a slinky. You're going to squeeze it in about the x-axis without changing the amplitude. Unless you could change the amplitude as well if you wanted to by multiplying something out front and by the x in front of the x. But we're just focusing on one translation type at a time. So yeah, so sine 2x, you can see 0. Pi over 4 is 1. Pi over 2 is 0. Then, yeah, so the period gets divided by 2. So the period before was 2 pi. Now it's going to be pi. We go 0, 1, minus 1, 0. 0, 1, 0. Okay, no. 0, 1, 0, minus 1, 0. 1, 0, minus. Now we restart the pattern. The period has been cut in half, which the graph's going to be a higher frequency, right? If you look at it that way, not angular frequency, it's going to be a higher, just standard frequency. Okay, now they say, what is y is equal to sine of 4x? Well, that's going to cut the period by a factor of 4. So you're going to go from 2 pi to pi over 2, right? It cuts the x-intercept locations down by a factor of 4, everything. It gets shrunk along the x-axis by a factor of 4. So these values suggest that one complete cycle is achieved in pi over 2 units, which is reasonable because sine of 4 times pi over 2 is, yeah, In general, the graph of a function of the form y is equal to sine bx or y is equal to cosine bx for b is greater than 0 will have a period different from 2 pi when b is not equal to 1. That's right. Because if you shrink or stretch a sinusoid about the x-axis, you're going to change the period. So if you multiply something in front of the x variable in the sinusoid function, that's what you're going to be doing. Okay, and that's pretty much it for this section as far as an introduction to the graphs of the sine and cosine functions. So we've talked about all of the terminology, all of the main features of these graphs. You have a sense of how they can be stretched or shrunk. And all they're doing for the rest of the section is guidelines for sketching graphs of sine and cosine functions. They're just working different examples of graphing the functions, which is important to do. And we're going to do this in upcoming videos. But this topic is so important. I'll probably make another video that'll come right after this one where everything that we just talked about in this video, I'll go through again, but we'll like draw it out on the graph, and I'll give another summary of it on the whiteboard. But yeah, so they're just working some graphing examples, and then here at the end they do a trigonometric model example. So the average temperature in Mold Bay, Canada can be approximated by a sine function. Yeah, so it's really important to get a sense for the types of phenomena in real life that you could think about modeling with a sine or cosine function. And so we'll work some examples in the upcoming video, but the more examples of this you see, I think you'll get a much better intuition behind how fundamental a pattern like a sinusoidal pattern is in nature. Here you can see that this sine function is shifted. It's shifted to the left or to the right. It's stretched along the x-axis. It's scaled along the y-axis. So yeah, this was just an introduction to the sine and cosine function graphs. We've got more videos coming up so we can really get more practice and look at these graphs in more detail, work some problems. So, okay, see you in the next video.